Hi guys, it's Mrs. Millison. Okay, let's tackle probability. I handed out this kind of overview sheet in class, and over a series of videos we're going to go through kind of what all of this means. So our first video today is kind of the basics. Okay, it'll be the basics of probability, and we're going to deal with mutually exclusive events. So mutually exclusive events are events that cannot occur at the same time. Okay, so we're going to go through the 5 basics of probability, and we're going to talk about mutually exclusive events where they cannot occur, events A and B cannot occur at the same time. So the probability of A and B occurring at the same time is 0, okay? And we will touch on this general addition rule when the and is 0 because the events are mutually exclusive. Okay, I get ahead of myself. So let's go through our 5 basics here. I think I have these written on another sheet of paper. Okay, so the first basic is that probabilities are numbers between 0 and 1, okay? And again, I've talked about that in my previous video, but we'll talk about it again. Okay, so probability of 0 means the event will not happen. Probability of 1 means the event will happen. A probability of 0.5, it could or it couldn't happen. Not gonna be surprised either way. Okay, probability of 0.9, probably going to happen. Okay, I would be a little surprised if it didn't happen, but still there's a 10% chance it might not happen, so I wouldn't be totally surprised. If a probability was 0.99, that's definitely going to happen, but there is a 1% chance it won't happen, but I would be very surprised if it did not happen. Okay. All right, so let's look at flipping a coin. Okay, so when we flip a coin, we only have 2 outcomes. We have the our outcomes are heads or tails. Okay, so the probability of heads is 0.5 and the probability of tails is 0.5. So again, either one could happen. They both have the same chance of occurring. Okay. Number 2 says the probability of all possible outcomes in an event must add up to be 1.0. Okay, well, if I add up 0.5 plus 0.5, it's going to equal 1.0. So these are the only possible outcomes when I flip a coin. Okay, and we'll do some other ones where we have more possible outcomes, but I thought this one was the quick and easiest way to demonstrate that. Okay. The third basic rule is probability equals the number of a specific outcome, a specific event, over the total number of outcomes, okay? So for this one, I wanted to flip 3 coins, all right? So let's start by listing all of our possible outcomes, okay? Okay, and on my probability review or overview sheet, I talk about different strategies, and listing all the possible outcomes is one strategy, and we're going to do a probability model also in a second. Okay, so flipping 3 coins. So I could get all heads, right? I could get 2 heads and 1 tail, and the tail could be the third coin, the tail could be the second coin, or the tail could be the first coin, right? I could get 2 tails and a heads, where the heads is the third coin, the heads is the second coin, or the heads is the first coin. And then the only other option I think I can get is all tails. So 2, 4, 6, 8. There's 8 possible outcomes, okay? So if I want to know the probability of a specific outcome, so let's say my event, and I'm going to denote it as A, is getting 2 heads, okay? So I would say the probability of A, so I'm just going to do the total number of that specific event, so 2 heads is right here, those 3, out of the total number of outcomes, which was 8. So the probability of getting 2 heads is 3 out of 8, okay? Now I can create a probability model where I have the number of heads when I flip 3 coins, okay? Well, the number of heads is either going to be 0 heads, 1 heads, 2 heads, or 3 heads, okay? So if I want to find out the probability of all these, so I'm going to do the probability down here. I already know the probability of getting 2 heads is 3/8, okay? So let's figure out the probability of getting no heads. Well, that's just this one occurrence, so that's 1 out of 8, okay? 1 heads are these 3, so that's also 3 out of 8. And then 3 heads is another 1 out of 8. So this is a probability model, okay? And I created that by listing all my possible outcomes. Okay, now if we go back to our other rules, the probability of all possible outcomes must add up to be 1. Do these add up to be 1? 3, 4, 5, 6, 7. Yep, this is 8 eighths or 1. Okay, so I know that this is a good probability model because all my the probabilities of all my possible outcomes, which was the number of heads, adds up to be 1. Okay, so that is rule number 3. Okay, so rule number 4 says the probability that an event does not occur is the complement of the probability of an event does occur. Okay, so if I know probability of an event has 0.75, the probability that the probability of its complement is simply 1 minus 0.75. So right here, I know the probability that I'm going to get 2 heads is 0.38. So the probability of not A, or probability of not getting 2 heads, should be 1 minus the probability of getting 2 heads. Okay, so if I do, let's see, 8 eighths, that would be 5 eighths. And if I think about that from my probability model, this is the probability of getting 2 heads, so the probability of not getting 2 heads are the other probabilities, so 3, 4, 5 eighths. Okay, but I can always do the complement of 1 minus. Okay, so those are my 5 basic rules. My 4 basic rules. We forgot the 5th one. Let's do the 5th one. If 2 events have no outcomes in common, we call them mutually exclusive or disjoint, you might say. I tend to say mutually exclusive. Sorry, I'm getting a glare on my papers. Then the probability of one event or the other event will happen is simply the sum of their probabilities. Okay, so let's do this again. Okay, so if I want to know the probability of getting 2 heads or 3 heads, okay, well, first of all, I can't get 2 heads and 3 heads. When I flip 3 coins, I'm either going to get 0 heads, 1 heads, 2 heads, or 3 heads. So getting 2 heads and 3 heads are mutually exclusive. I can't get them both in one roll, on one flip of 3 coins, okay? So the probability of 2 heads and 3 heads is 0. There's no way I'm going to get 2 heads and 3 heads when I flip 3 coins, okay? But I can get 2 heads or 3 heads. So in order to find that, all I have to do is add up the probability of 2 heads and the probability of 3 heads. So the probability of 2 heads is 3 eighths, and the probability of 3 heads is 1 eighth. So the probability of getting 2 heads or 3 heads is a half. Okay, so 4 eighths, 1 half, or 0.5. Okay, so when I flip 3 coins, there's a 50% chance that I'm going to get 2 or 3 heads. Okay, there's a 0 chance I'm going to get 2 heads and 3 heads because they are mutually exclusive. They can't occur at the same time. Okay, so those are my 5 basic rules. And I touch on my general addition rule. Okay, so the probability of an event, or event A or event B, is simply the probability of event plus the probability of event B, probability of event A plus the probability of event B minus any overlap when the events happen at the same time. Well, if my events are mutually exclusive, then overlap is 0, and I don't even have to worry about it. All I'm going to do is add up the events. Okay. We'll get to these other ones later. All right, let me do a couple more examples of mutually exclusive. Where's here we go. Okay, let's do a couple more examples of mutually exclusive. Sorry, the sun is starting to put a glare on my paper. Okay, hopefully the glare won't bother. Okay, blood type. Blood types for people in the U.S. have the following distribution. There's 44% type O, 42% type A, 10% type B, and what percent has type AB? Okay, well, I'm not going to write out all possible outcomes because these are all in percentages, but I am going to create a probability model. Okay, so I'm going to write blood type and then the probability. So my possible blood types are type O, type A, type B, and type AB. So if 44% of the U.S. population is type O, then there's a 0.44 probability that a randomly selected person is going to have type O blood. Type A would be 0.42 and type B would be 0.1. Okay, so how would I figure out the probability of that a randomly selected person is going to have type AB blood? Well, if I go back to my probability rules, the probability of all possible outcomes in an event must add up to be 1. Okay, so I know these all have to add up to be 1. So the probability of AB is simply going to be 1 minus all the other probabilities added up. Okay, what is that? 86, 96, so 0.04. Okay, so now I can fill that in. So that one rule can help me fill in a missing item in my probability model. Okay, so now let's just do a couple probabilities. So I want to know the probability that a randomly selected person is going to have type O blood. I just go to my my model here, and again, these are mutually exclusive because a person can't have type O and type A. Okay, let's do a complement. What's the probability a randomly selected person will not have type O blood? So I can do the complement. I can do 1 minus 0.44. Okay, 1 minus 0.44 is 0.56. Now again, there's my type O. The probability they're going to have not type O is that they're going to have one of these other three. So if I added these up, these would also be 0.56. Okay, but we can do it a little quicker with our complement. Okay, let's do the probability that somebody's going to have type O and type A blood. All right, well, again, mutually exclusive. There's no way somebody's going to have type O and type A blood. So this is 0. Okay, now what's the probability somebody's going to have type O or type A blood? That is possible. Okay, so that goes back to our general addition rule, where all I have to do is add the individual probabilities. I don't need to worry about the and because they're mutually exclusive. There is no and. Nobody can have type O and type A. So I'm just going to do the probability of type O plus the probability of type A. So O is 0.44, A is 0.42, so what's that, 0.86? So there's a 0.86 probability that a randomly selected person will have type O or type A blood, okay? And if you think about mutually exclusive events from a Venn diagram, there's no overlap. I would just have the 4 bubbles with the different types of blood. And there's no overlap because nobody can have both types of blood or 2 types of blood. Okay. All right, let's do one more example. This one had our proportions. Let's do one where we're given counts, so we have to figure out our proportions. Okay, we asked 200 students their class designations, freshmen, sophomore, juniors, or seniors. 61 are freshmen, 56 are sophomores, 45 are juniors, and 38 are seniors. Well, first of all, if I know these are mutually exclusive because a student can't be a freshman and a sophomore at the same time. Sorry, my light is driving me nuts. Let me move this up a little bit. Try to get away from the light or the glare. Okay, so I know I asked 200 students, so I'm going to put the class and the probability. Oops, didn't mean to put that there. Class and probability. So I'm going to have freshmen, sophomore, juniors, and seniors. Okay, and again, one of my strategies is to create a probability model. So I know they're all out of 200 because I asked 200 students. Okay, 61 said they were freshmen, so the probability that a randomly selected student is going to be a freshman is 61 out of 200. 56 were sophomore, so 56 out of 200 is the probability someone's going to be a sophomore. Juniors is 45, and seniors is 38. Now, I should add these up to make sure they equal. Oh, whoops, just knocked my phone. Oh, good heavens, guys. All right, let me add these up to make sure it adds up to be 200 because I got to make sure it's a legit probability model. And again, 200 over 200 is 1. And then I can turn these into decimals, okay? So if I do 61 over 200, I can turn these numbers, these fractions, into decimal probabilities, okay? So this one's 0.28, 0.225, and 0.19. And again, if I add those all up, it equals 1.0. So now I can easily answer the questions. What's the probability someone is a senior? The probability someone is a senior is 0.19. What's the probability the randomly selected person is not a senior? So my complement would be 1 minus 0.19, which is 0.81. And again, if I added up those other three, it would also equal 0.81. What's the probability that a student is a junior and a senior? Well, again, these are mutually exclusive. A student cannot be a junior and a senior at the same time. So this has to be 0, okay? But I can do the probability that a student is a junior or a senior. And again, if I go back to my probability, my general addition rule, my or will simply be the two individual probabilities added up, and I will subtract the and, but again, these are mutually exclusive, so my and is 0. There is no overlap, okay? So I will write the probability of a junior plus the probability of a senior minus the probability of junior and senior. But again, I know that's 0, so I don't have to worry about that. So the probability of a junior is 0.225. Probability of a senior is 0.19. So the probability of a junior or a senior is 0.415. Okay, so these were so again, mutually exclusive events. The and will always be 0 because you can't be in one of the two. You can't be in two categories at the same time. But you can always calculate an or by simply adding up the individual probabilities. And you don't even have to worry about the and, subtracting the and because it's 0. Okay, so hopefully this was helpful. What we covered in this video were our 5 basic probability rules, and we touched on our general addition rule in the case of mutually exclusive events. Okay, so I will talk about dependent and independent events in another video. So hopefully this was helpful. Oh, and we also talked about our strategies of listing all possible outcomes and creating probability models, okay? Probability models we generally see with mutually exclusive events. Listing all possible outcomes, they can be dependent and independent events, and I'll talk about that in the next video. Okay, hopefully this was helpful, and I will see you all later.